In order for us to use the force and moment balance equations of statics to solve for the unknowns in a system in equilibrium, the system not only has to be rigid and static, but the number of unknowns that we're trying to find must match the number of equations that we have available from the force and moment balances. Remember these three examples of pin-jointed trusses, trusses that are where the members are free to rotate at their joints. This system here is unstable because it doesn't have enough unknown reactions to maintain the system in equilibrium. There are only two unknowns in the system, but we have three criteria that must be matched. This system can be in equilibrium, and the number of unknowns and the number of equations will match, and so we have a system that's statically determinate. If we add another unknown to the system, now we have more unknowns than equations, and so the system becomes indeterminate. It doesn't mean that it's not in static equilibrium, just that the equations of force and moment balance alone are insufficient to solve for the unknown reactions and forces. Now in these pin-jointed trusses, the unknowns were reaction forces but not moments, because pin joints can't resist a moment, and in that way they're similar to joints in our body that require the actions of muscles to keep them stable. Different types of joint or constraint allow different kinds of reactions. A support with rollers on a fixed surface allows for a vertical reaction force, but not for a horizontal force or a moment. So in 2D there would only be one reaction, or in 3D. Similarly, a collar sliding on a shaft with a pinned attachment also allows only one reaction force perpendicular to the shaft, but not a tangential reaction force or a moment, again in 2 dimensions. If the bar is pinned to a fixed support, then in 2 dimensions there will be a vertical reaction force and a horizontal reaction force, but no moment reaction will be possible because the bar can rotate about the pin. If the support is fully fixed and clamped, then this will allow for a horizontal and a vertical reaction force and a reaction moment. So 3 reactions in 2D, or 6 in 3D. 1 reaction moment in 2D, 3 reaction moments in 3D. So let's look at the equilibrium of a 2-dimensional static rigid structure. Our structure has 9 members and has a pinned support at the left end and a pinned support on rollers at the right hand end, 3 applied external force vectors plus the weight, and we'll label the 4 corners of this structure A and B at the supports and C and D on the top. In 2 dimensions, the force and moment balance equations, which are sigma F equals 0 and sigma M equals 0, reduce to 3 equations because in 2D the Z component of the force is 0 and the X and Y components of the moment vector are 0. So the force and moment balance equations for a static equilibrium in 2 dimensions reduce to the sum of the X forces equals 0, the sum of the Y forces equals 0, and the sum of the moments about a point O equals 0, where O is any point on the plane of the structure. This means that we can only solve the system for 3 unknown reaction forces and moments, given prescribed applied forces and moments and the known geometry. Although we cannot use additional equations, we can use equivalent equations. So, for example, instead of using the sum of the x components of the force equals 0, and the sum of the y components of the forces equals 0, and the sum of the moments about point A equals 0, we could equivalently use that the sum of the x components of the forces equals 0, the sum of the y components of the forces equals 0, and the sum of the moments about point B equals 0. Or, equivalently in this problem, we could actually use that the sum of the x components of the forces equals 0, the sum of the moments about point A equals 0, and the sum of the moments about point B equals 0. Now, having solved for the reactions in this structure, we could also make a new free body diagram by making cuts in the structure to expose forces in the individual members and see if the resulting system or subsystem is itself statically determinate, and then use the force and moment balance equations to solve a new problem for the forces in each of the members. But let's start by drawing the free body diagram for the whole structure so that we can set up the problem to solve for the unknown reactions. So here's our structure again. The components of the applied forces are Py and Px, Qy and Qx, Sy and Sx. In addition, we can add another force vector representing the weight of the structure acting through the center of mass. The components of the reaction forces are Ax and Ay at A, and By at B. So, observe that because of the types of the reactions, we have 3 unknowns and 3 equations. The system is thus statically determinate. We have enough equations to solve for the 3 unknowns. But what if the system had different constraints? For example, what if the supports were pinned at both ends but without rollers? Now the free body diagram would look similar. We have the same applied force components, including the load due to the weight. And we have the same x and y components of reaction forces at A. But now on B, we have x and y components of reactions, so we have 4 unknown reactions and only 3 equations, so the system is indeterminate. In this case, again, we have the same applied loads, but this time, both supports are on rollers. So now in the free body diagram, we have the same components of applied load and weight, but now only 2 reaction forces instead of 3. So now we have more conditions to meet than unknowns to meet them, and so the system is only partially constrained, and in fact cannot necessarily be in static equilibrium because there's no reaction force to balance the applied y components of force on the structure. Here's another example, again with the same loads, and again with supports on rollers, but this time with 3 supports instead of 2. So this time in our free body diagram, the applied loads are again the same, but we have 3 reaction forces, which is the right number of unknowns, but there's no reaction again to balance the y components of the applied force, so the system is not properly constrained and would not be able to be in static equilibrium. So none of these three last cases is statically determinate. Next time we'll learn how to use the equations of force and moment balance for structures in static equilibrium to analyze the forces, moments, and reactions in skeletal joints.